Today we're going to talk about acceleration and look at an example problem. Let's take a look. So acceleration, it's really the rate at which you are changing your velocity. Okay? And from an equation standpoint, we're going to have the average acceleration is going to be the change in velocity with respect to the change in time, or divided by the change in time. Don't forget that delta symbol, or delta V, is really talking about the change in, and it's always going to be final minus initial. So here we have the change in velocity over time, or final velocity minus your initial velocity. From a unit standpoint, let's see if we can actually figure out what we're doing here. So velocity, do you remember what the units are for velocity? And with respect to time? Okay, well that's right. It's meters per second divided by second, or meters per second, which really is often referred to as meters per second squared. Okay, it's meters per second, so it's a good way to remember the change in velocity per time. But meters per second squared is really the way that it's represented and is as the base SI unit. It also, acceleration is a vector. It has a magnitude and a direction. Where is it picking up that direction from? Well, it's really that change in velocity. So velocity is a vector that came from displacement because you're changing position, and now you're changing your velocity and causing an acceleration. So depending on how that velocity changes will determine the direction of your acceleration vector. And this can be both positive or negative, just like any other vector. Direction here is can be defined by positive or negative sign when we're talking about it mathematically. Alright, so let's take a look at an example here. My daughter Madison was nice enough to help me out with this video, so let's take a look. Maddie was riding her bike in the driveway at 2.84 meters per second. And after applying the brakes for 0.90 seconds, she came to a complete stop. What was her average acceleration? I was able to use a video analysis software that's called Capstone. That's made by Pascal. This is a software that you guys will use for not only video analysis but also data capturing when doing our labs this year. And you can see here that I was able to actually track Madison's motion on her bike and create markers that would ultimately then create a graphic chart that I could use, which was a position versus time graph. Graphical representations of motion is something that we're going to continue to learn about in greater detail. But I just wanted you to understand that this helped me to analyze her speed and how long it actually took for her to come to a complete stop. So let's look at the problem and break it down. Okay, so first what we need to look at and say, well, there's a change in velocity here. It's 2.84 meters per second. And that happened over a change in period of time of 0.9 seconds. I'm going to ask you guys right now, we mentioned it before, but do you remember the 3 steps that I want you to follow when analyzing and solving problems? Yes, the first step is in fact to write the equation in variable form. The second step is to plug in the numbers, and the third step is then to go ahead and solve the equation. That first step of writing out the equation in variable form, it's going to be something that you guys are going to struggle with, and it's really important that you take the extra seconds. These problems right now are very simple and straightforward as we're learning new processes here, but the complication of the equations will get more, and so writing out the equations in a variable form is really important. Alright, so what is our equation? Well, acceleration is a change in velocity with respect to time, change in time. Well, we have both of these variables here, so let's go ahead and plug in. 2.84 meters per second divided by 0.9 seconds is going to give us 3.15 repeating, which with significant figures of 2 is going to give us 3.2 meters per second squared. Now, looking at that answer, that's actually not right. That can't be correct. Does anybody see where we actually might have went wrong? Well, let's go back here and restart the problem and see what we can find. Well, when we're identifying our known values, that 2.84 meters per second is not actually the change in velocity. It's the initial velocity that she was traveling with. right before she applied her brakes. And then after applying her brakes for 0.9 seconds, so that's still the same, her final velocity after the 0.9 seconds was 0 meters per second. And how do we know that? Well, the problem tells us that she came to a complete stop. So you have to be very careful in reading the problem and identifying your known values. All right, same equation that we had before, but except this time I've actually expanded it to the complete version of that, okay? That change in velocity, that delta V, is really final minus initial. So in this case, now that we've identified initial and final velocities, we can plug those variables in. And so it's 0 minus 2.84 meters per second, still divided by the 0.9 seconds. And this causes us to have a negative 2.84 meters per second in terms of our change in velocity, as before it was positive 2.84. Still doing the math, we end up with negative 3.2 meters per second squared using significant figures. So the first time we had 3.2 meters per second squared. This time we have negative 3.2 meters per second squared. Does that make sense? Well, she came to a stop. She was actually slowing down. She was traveling to the right. Notice that this problem didn't really talk about north, south, east, west, right or left. It just kind of gave you the information. And you're going to get problems like that. So in this case, in the video, she was actually moving to the right and her velocity was given as a positive direction. So the direction that she was traveling in was identified to be 2.84 positive. So for her to actually slow down, she had to have an acceleration that was in the opposite direction. If she had her acceleration in the same direction, that would have actually caused her to speed up. So it doesn't really matter the fact that the acceleration is negative in this case. What's important is that it's the opposite sign or direction with the way that she was traveling. If the problem showed Madison traveling to the left and was given as an initial velocity of negative 2.84 meters per second, then her acceleration would have had to have been positive 3.2 to cause her to stop. Again, in the opposite direction that she was traveling. And if you look at it mathematically, if it was negative 2.84 as her initial velocity, it would be 0 minus a negative 2.84, which those negatives would cancel and cause it to be a positive 2.84 for change in velocity. So let's recap. We learned that the average acceleration is the change in velocity with respect to change in time, or final velocity minus initial velocity over the change in time. And that acceleration is a vector with both a magnitude and direction. Acceleration can be positive or negative. And that when your object is speeding up, that means that the velocity and the acceleration vectors are in the same direction. Both could be negative or both can be positive, but they're in the same direction. Slowing down is in fact the opposite. Your velocity and acceleration have to be in opposite directions. Again, doesn't matter which way you're actually traveling, your acceleration has to be in the opposite direction of which you are traveling to cause you to slow down. Thank you, and I'll see you soon.